This is a question about alkenes. It's a 7 marker. There are 3 sections to it. I'm going to recommend you try it, and when you've done it, review the rest of the video. Here's part A, part B, and part C. Okay, so taking a look at part A, we are outlining the mechanism for the formation of the major product. Now we need to start by making sure that 2-methylbutyene is drawn out correctly. So I have that. We know we're using H2SO4, but when we're doing this mechanistically, we have to show it in a different way. So I'm going to use HOSO3H. Some people will use OSO2OH. It's whichever you're more familiar with. Now for the mechanism, I've then got to start thinking about what's going to attack where. And in the H2SO4, I've got a delta positive H. Now that means that it's going to attack the electron-rich double bond. Here's the difficulty. You've got to remember that the arrow will always represent the direction of electron flow. It will always go electron-rich to electron-deficient. So my curly arrow, my first mark, goes from the double bond to the H. Now, realistically, what that means is I've formed a bond between a C and an H. So the H can't have a bond to the O in the OSO3H. So my second arrow goes from the bond to the OSO3H. Now at this point I'm going to start building the intermediate, but you'll notice I've broken the double bond and I've not added anything new. Actually, for the major product, for reasons we will get to on part C, the H will be on the left-hand carbon from the double bond, whereas my positive ion, my carbocation, will be on the carbon that has got the 3 alkyl groups coming from it. Makes it a tertiary carbocation, so hopefully that's ringing some bells for you, ready for part C. But I've still not finished the mechanism. I need OSO3H, but if I write it like this, I'm going to lose marks, because it's now an OSO3H minus ion. But if I write it like this, I'm still going to lose marks, because I've got to include the lone pair of electrons. We know that curly arrows represent the movement of electrons from electron-rich to electron-deficient, and hopefully it's very, very clear here that the electron-rich is the lone pair, and the electron-deficient is the positive carbon. For this, you'll get 1 mark for each of the 3 arrows and 1 mark for correctly drawing the intermediate structure. Now, in terms of the minor product, let's go back to where I was starting with my intermediate. It's going to be the other way round. So the H will have added onto the carbon surrounded by 3 alkyl groups, leaving the OSO3H joining on with the carbon on the right-hand side. The big question is why, and that's what C is really getting at. And if you take a look at what you've drawn out in your answer, the major product is formed via a tertiary carbocation intermediate. Now that means that the positive carbon is surrounded by 3 alkyl groups. The minor product was only surrounded by 2 alkyl groups and an H, so it's a secondary carbocation intermediate. And tertiary carbocations are more stable. It's because of something called the inductive effect, not asked about on this question, but could be elsewhere. And because it's more stable, it means that it can exist for long enough for the OSO3H- to come and join it. So there's your 2 marks.